inverter? Inverter is a power electronic circuit that converts a DC voltage into AC voltage. That is the first point. The second point is that inverter make use of switches. In inverter circuit, you are having switches that are arranged in some particular pattern. Okay, so like how, what is the purpose of the switch? The purpose of using a switch in any of the electrical circuit is to control the power flow. Switch is used to control the power flow. Okay, so here two switches are connected in series. This is what we call it as half bridge configuration. So, and two sources are connected in series. So, these are the interconnection points of sources and switches. So, both the ends of the series connected switches are connected to in parallel to the sources, and the midpoints, at the midpoint the voltage is measured. At the midpoint the voltage is measured, and the positive terminal is taken nearer to the switch, and negative terminal is taken nearer to the source, so that the switches are named as S1 and S2. The point what you need to remember is this is called as a leg. A leg contains two switches. Two switches in it. So the switches are operated in such a way that the pulses are applied to switches in such a way that when S1 is on, during that time S2 should be off. Similarly, vice versa. That means when S2 is on, S1 should be in off state. This is the condition for operation of any kind of inverter. So what is the operating condition? The leg in basic inverter contains two switches. These switches are numbered as S1 and S2 or 1 and 2. When one switch is on, other switch should be in off state. Other switch should be in off state. That means the trigger pulses, the same trigger pulse that was generated for triggering S1 can be complemented and given as input to the second switch. So this is what. Now we see this is the basic circuit diagram for half bridge inverter with resistive load. So you know that the load current here, it is not IL, it is I0, and the voltage across the load is V0, and here the load that I considered for analysis is resistive in nature. Resistive in nature. You know that resistance load is the basic load with which we can start analyzing our circuit. Okay, so the switches S1 and S2 are operated in complementary manner. What is meant by complementary manner? You have studied logic circuits in your switching theory and logic design. Okay, you take the NOT gate. What this NOT gate will give you? So if you give A as input, the output of this NOT gate is complement of A. So if X is the input and Y is the output, then for a NOT gate, if X value is high, the high is represented with 1, Y value would be low. The low logic is represented with 0. If X is low, then Y is high. Okay, so 1 is representing as on state, 0 will represent off state of a switch. So when the switch S1 is on, S2 must be off, and when the switch S1 is off, S2 should be on. So this logic is called complementary logic. This logic is called complementary logic. So now we see how to realize the sources, this VDC and switches. These switches are realized with the help of IGBTs or MOSFETs. The switches S1 and S2 are realized with the help of IGBTs or MOSFETs. So this was the basic circuit diagram for a half-bridge inverter with resistive load. The switches are realized with the help of a transistor connected in parallel with an anti-parallel diode. Q1 and D1, this represents the combination switch S1, and this combination Q2 and D2 represent switch S2. So whenever you are applying trigger pulses to Q1, you are not supposed to apply the same trigger pulse to Q2. That is what meant by complementary logic. And this is the interconnection point, and it is represented with A. And here we are making use of two capacitors connected in parallel with the source. So that what happens, you know that if you connect a capacitor, a bare capacitor across the voltage, across the terminals of a DC voltage source, the capacitor C will act like a voltage source. So that if I take C1 is equal to C, that means equal value of capacitors are connected in parallel with the source. And what happens? Voltage across VC1 is equal to voltage across VC2, because the magnitudes of capacitor C1 is equal to C2. As these two are connected in parallel with the source, this value is equal to Vs by 2. That means exactly half of the voltage will appear across capacitor C1 and C2. So this is treated as the source. So in between the middle point of the source and the switches, the load is connected. So because I told you that the lower potential terminal is connected or considered at the source side, so that is the reason why I represented this with 0, and the higher potential side I represented with A. So that VA0 will become my load voltage, or output is measured between the terminals VA0. This value is considered to be V0. So V0 is positive only when if A is at higher potential in comparison with 0. A is at higher potential with if the potential of point A is with respect to O. The potential of point A is lesser with respect to 0. So in such cases, the load voltage is considered to be negative. And we assume that the switches are operated with a time period or with a frequency F. I'm operating the switches with a frequency F, so that the time period of the switch operation is equal to 1 by F seconds. So frequency is measured in hertz. So the frequency of circuit operation is fH, and the time period of the output voltage is equal to T. This T is the reciprocal of frequency. So you know that the reciprocal of frequency can be written as 1 by f. So this value is in seconds. So that Q1 is switched on for time t by 2 seconds, and Q2 is, or S2 is S1 and S2. Here Q1 and Q2. S2 is switched on for time t by 2 seconds. So that both the switches are operated for a period t by 2, t by 2 is equal to t seconds. So when Q1 is on, then Q2 must be in off state. When Q2 is on, Q1 should be in off state. So the total time is equal to t seconds. Now, how we apply this equation for a frequency of 50 Hz? In my house or in your house, you need to produce a voltage of at an alternating voltage at a frequency of 50 Hz. An alternating voltage at a frequency of 50 Hz. So my frequency of operation will become 50 Hz. Then the time period is 1 by f. That is equal to 1 by 50. You know that 1 by 50 is equal to 20 milliseconds. So S1 should be on for 20 by 2. T is equal to 20 seconds, 10 milliseconds. And S2 should be on for 20 by 2, 10 milliseconds. So 10 plus 10 is equal to 20 milliseconds. Like this, we can get the required time period for generation of the trigger pulses that are applied to switches S1 and S2. That means you need to just apply a trigger pulse that is having a minimum width of 10 milliseconds to S1 and S2 also. But the trigger pulse that is supplied to S2 should have a time delay of 10 milliseconds. Should have a time delay of 10 milliseconds. This time delay on time and off time you can clearly understand from the concepts of signals and systems, because you are studying the course signals and systems or subject signals and systems. From there you can come across through the word pulse waveforms. Okay, so a pulse having a width of 20 millisecond, a pulse having a width of 10 millisecond with a period 20 millisecond is applied to S1, and whereas for S2, the same pulse having a time period of 20 millisecond with 10 millisecond, but having a phase delay of 10 millisecond is to be applied to switch S2. That we see on time scale for the sake of understanding. So any pulse whose magnitude is measured, the time duration is measured from the origin. So this is the origin. On this origin, I am representing the time scale. Okay, the time is in milliseconds. So suppose if I want to apply the trigger pulses to S1 and S2. So I need to have a pulse having a width of 10 milliseconds. This is high and this is the low logic. So this is how the trigger pulses are applied to S1. Similarly, when this is off state of the pulse, off value of the pulse, this is the on value. This is the on value and this is the off value. So for S2, when S1 is supplied with a pulse having off value, then it should be on. So this is called as delay. This is called as delay. So the trigger pulse, this is called the time period. And this is called as width of the pulse. This is also the width of the pulse. Width of the pulse is nothing but the time for which the pulse is having high value. Okay, so if you observe the pulses that are applied to S1 and S2, both are having the same time period. Both are having same time period and same width. The same width. So this is a pulse width time period equal to 20 milliseconds. Suppose if we consider a general case, the general case is time is measured in seconds. For a general case, the time is measured in seconds. So what happens? This will become T by 2, and this is equal to T. This is 3T by 2, and this is equal to 2T. So 2T, 3T by 2, T by 2. So the pulses that are applied to T2 will be like this. So this is what the conceptual point of view that you should never forget. You should never forget. So because why I am point is, while I am explaining you the concept of inverters, a full bridge inverter and three-phase inverter, these time delays are very important. These time delays are very important. Okay, so S2 is triggered with a time delay of T by 2 seconds, having a pulse having a time delay with T by 2 seconds, but whose width is equal to same as that of the pulse that was applied to switch S1 and have the same frequency. So now we see the operation of the circuit. For a time in between the time interval t less than small t less than T by 2, S1 is on and S2 is off. Because of that, what happens is Q1 is on and D1 is off. Because S1, this switch is realized with the help of a diode like this and a transistor connected like this. These two are connected in parallel. Q1 and D1, this is connected to a capacitor across this, which is charged to a voltage Vs by 2. This is 0 and this is A, this voltage V0. So the upper terminal of the capacitor is charged to positive polarity, lower terminal is charged to negative polarity. As a result of that, this diode D1 will get reverse bias. The diode D1 will get reverse biased. So what happens is the value of voltage V naught, that whenever the switch is on, the on-state voltage drop of switch, ideal switch, can be considered equal to 0, so that no voltage drop appear across the switch, so that the terminal A is connected to the positive terminal of the supply and O is already connected to the point O, so that voltage across the load V naught is equal to Vs by 2, and the load current I naught is equal to current flowing through the transistor 1, which is equal to V naught by R. The value of V naught is equal to Vs by 2 into R. So the current I naught is equal to Vs by 2R. You know that this Vs is a constant, because if you take a large capacitance, value of capacitance is very, very high. If C is high, the value of C is high, then what happens is the voltage that the capacitor will take very less time to get discharged. So how can I say that the value of C is very high? We have studied the time constant, because if you observe, this behaves like a series RC circuit. So the time constant of series RC circuit is R into C. So if you choose this value of C in such a way that this time constant is much more higher than the time for which the switch is on, then what happens? The capacitor will discharge very slowly. Because of that, what happens? The capacitor voltage will remain at a constant value that gives a constant magnitude of voltage. A constant magnitude of voltage applied across a resistance will result in constant magnitude of current to flow through it. So if we draw variation of V naught with respect to time t, then the switch is on for a period t by 2, whose value is equal to V naught or Vs by 2. This is the voltage. So I am taking the time interval 0 less than t by 2 as mode 1. Okay, during mode 1, S1 is on and S2 is off. So in this, during this mode 1, the load voltage is positive. The load voltage is positive. Okay. So now we try to analyze the circuit operation when switch S2 is on. During the time interval, switch S2 is on. In which time instant the switch S2 is on? For the time t by 2 less than t, this we treat as mode 2 of operation. Mode 2 of operation. During this mode, S2 is on. So S1 is on. Off. Sorry. During mode 2, S1 is on and S2 is on and S1 is off. S2 is on and S1 is off. So what happens during this mode? This is point O and this is point A. As S1 is off and the switch 1 is off, this is S1. Okay, so here we have realized the switch S2 with the help of a transistor Q2, connect a diode connected in parallel with this Q2. Okay, so this is the load current I naught Vs by 2, positive and negative. Then what happens is the Q2 is on and D2 is off. If you observe, the diode D2 is connected to the positive terminal of supply. Diode DT is connected to the positive terminal of the cathode of the diode. This is cathode and this is anode. The cathode terminal of diode D2 is connected to positive terminal of the battery or the source. As a result of that, diode D2 is open circuited. Now, you know that always the current flows from higher potential terminal to lower potential terminal. So the direction of current in load will be from O to A. In the previous case, the current is flowing from the terminals A to O. If you observe, the current is flowing from A to O because terminal A is connected to a positive terminal, so the current will flow from A to O. But in this case, A is connected to, this is A. The switch S is closed. Switch S2 is closed. As a result of that, this terminal A is connected to the negative terminal of the source. As a result of that, what happens? V0 is equal to minus Vs by 2. And I0 is equal to, this current is I2. I0 is equal to, I2 is equal to minus Vs by 2R. It is equal to minus Vs by 2R. So if we draw the values of these voltages here is equal to minus Vs by 2, and the switch S is on for the time period up to T. So what happened? We have not changed the polarities of the input source, but the voltage that is available across the load terminals is reversed. The voltage that is available across the load terminals is reversed. This is how a constant magnitude DC voltage can be converted into an alternating voltage. And this sequence of operation will be repeated for infinite time intervals, for infinite number of time periods. As a result of that, the voltage would be like this. This is 3T by 2. Again, from 3T by 2 to T, 2T it is. And you will get a repeated square pulse. So the output of a half bridge inverter is a square pulse. The output of a half bridge inverter is a square pulse. Whether it is half bridge inverter or full bridge inverter, the output of a inverter is a square pulse. The output voltage is always a square pulse because we are giving a DC voltage, or we are applying a DC voltage, or we are using a DC voltage as a source. Is a source. So this is the instant where S1 is on and this is S1 is off. So when S1 is on, S2 is off. When S1 is off, S2 is on. So that this voltage is equal to Vs by 2 plus Vs by 2 minus Vs by 2. During the time interval 0 to T by 2, the voltage is positive, load voltage is positive, our voltage available across the output terminals is positive, and during the mode 2, the voltage available across the output terminals is negative. So this is repeatedly happening as the time is approaching infinity. Now, these are the values of load voltage and current flowing through I1 and current flowing through I2. Switch 1 and switch 2. Okay, and this is the fundamental component of the current. That is what we are supposed to get. But because if the load is resistive, this theta 1 will be started 0. This is called as the phase delay. This is called as phase delay. This phase delay will cause whenever the load that was connected across the output terminals is resistive and inductive in nature. But we never use resistive loads, resistance as load for any kind of inverter circuit, because most of the loads that we see in real time in our daily life are inductive loads in nature. That means each load will contain some inductance in it. Each load will contain some inductance in it. So we use RL loads. It means 95% to 99% of the loads are RL in nature. They contain some inductance in it. Only very few loads will be treated as resistive loads. The example for resistive loads are filament lamps. These filament lamps are considered to be pure resistive loads because this filament is made with tungsten, which contains only resistance in it, no inductance in it. So in modern days, usage of these filament lamps has brought down to very minimum. Except the application requires, demands, there we use these filament lamps. Because of this, due to the energy conservation techniques, all these filament lamps are replaced with LED lamps. So this LED lamps contains choke in it. This choke is nothing but an inductor. So what we have done, whatever even the 5% minimum loads that filament lamps that we are using, they are replaced with LED lamps. That we replace with these LEDs. They could take some filaments or some chokes in them. Okay, so this is what the shape of the current that we are supposed to obtain, but the shape of the current what we are obtaining here is a pulse. Is a pulse. So the points that you need to remember is in a half-bridge inverter, each leg contains. Half-bridge inverter contains only one leg in it. Only one leg in it. A leg contains two switches connected in series. The leg contains two switches connected in series. When switch S1 is on, S2 should be in off state. When switch S1 is on, switch S2 should be in off state. And vice versa. When S2 is on, S1 should be in off state. So when the upper switch is on, the load voltage would be positive. When the upper switch is on, load voltage would be positive. And when the lower switch is on, load voltage will be negative. Load voltage will be negative. So the load current I0 is equal to voltage applied across the load divided by the resistance value. Divided by the resistance value. So if V0 is equal to Vs by 2, then load current during S1 is on is equal to Vs by 2R. When S2 is on, the load voltage will be negative. That makes the load current to become negative. So that I0 is equal to minus Vs divided by 2R. Here, the shape of the voltage, that is voltage and current, that is available across output terminals is pulsating in nature. The shape of the voltages and currents that are available across the output terminals are pulsating in nature. That means we can get a square pulse or rectangular pulse. Square pulse or rectangular pulse across the output terminals of inverter. Across the output terminals of an inverter, whether it may be a half-bridge inverter or full-bridge inverter. So far we have analyzed the operation of half-bridge inverter supplying resistive load. Now, what is the time now? So now we see operation of half-bridge inverter supplying resistive load. There is no difference between these, as far as the circuit is concerned. There is no difference between the load, the circuit configuration, but the load what we connected here is RL in nature. In place of resistance, we considered resistance and inductance. So the circuit is realized like this. So that the direction of I2 is like this. If I2 is flowing in this direction, it is considered to be positive. But its value may be a voltage V0 by R when the switch S is on. The same during mode 1, S1 is on. Because of that, what happens? The current flows through I0 will increases slowly and reaches a peak value and then decreases. At T by 2, T is equal to T by 2, what happens is this I0 may not become 0. But Q2 is turned on. Thyristor Q2 is turned on. As a result of that, what happens? This diode D1 will start conducting. Because of that, the direction of I1 will get reversed. The direction of current I1 will get reversed. So that we will get a negative value of I1 at of time beyond T by 2. This I1 value will become 0. Because of that, this diode D1 will get reverse bias and conduction will continue, and this I2 will be contributed, and it increases in the reverse direction to a maximum value, then decreases towards 0, and at T is equal to T, capital T, diode, switch S1 is turned on and S2 is turned off. But because of the current has not become 0, this I2 will be diverted through diode D2, and it will continue up to some instant of time. By that time, this I1 will come into picture, and this current increases to a maximum value like this. So the operation of half-bridge inverter with RL load we see in next class.